From the very beginning, there was a dream for a trust layer for the digital future. But in 2012, the technology to achieve such a vision simply did not exist.
It really should be possible for anyone to just kind of wave their hand and carve out a piece of cyberspace and create a world of their own.
3 years later, in 2015, the Hashgraph consensus algorithm was born. In the same year, Mance and Lehman founded Swirlds to bring Hashgraph to life. In August 2018, the Hedera mainnet goes live, minting 50 billion HBARs.
We are about to launch the Hedera mainnet and mint 50 billion HBARs. There will never be another HBAR. This is it. Are you ready?
I'm ready.
Let's do it.
All right.
That's it. Congratulations.
Yep. Mainnet is live.
In 2019, we announced the Hedera Council to help govern the network, ensuring stability, decentralization, and responsible decision-making globally. On February 13, 2020, Hedera Consensus Service launches on mainnet, marking a new era. 1 year later, Hedera Token Service enabled native tokenization on the Hedera network. With billions of real-world transactions, Hedera has begun to cement itself as a leader in enterprise blockchain. To continue its impact in the digital economy, Hedera creates Stablecoin Studio, an open-source toolkit helping organizations integrate stable digital currencies seamlessly. Through another toolkit, Asset Tokenization Studio is helping making asset tokenization seamless, scalable, and secure. Hedera has taken a bold step forward by contributing its codebase to the Linux Foundation's Decentralized Trust initiative and introducing the Hedera Foundation and Hedera Council, realigning our ecosystem to unlock greater clarity, leadership, and purpose. Looking ahead, Hedera continues to lead with tokenization, digital economies, and beyond. What future will you build?
Hello, everyone, and welcome to this month's community call. This is the Hedera Technical Community Call for May of 2025. My name is Ed Márquez. I lead developer relations for Hedera at Hashgraph, and Hashgraph is that organization, that firm leading engineering and marketing initiatives for the Hedera network. And so today we have a fascinating array of topics to bring to you. But before we get into those topics, I want to cover a few things about housekeeping. The first one is that this is being streamed to multiple platforms and multiple channels. So please retweet, amplify, share it with your network. The second is that this is also being recorded. And so if you want to share it later on with friends, colleagues, or your network, you can do so. Or if you want to watch it later on at a faster speed or at a more convenient time, that's also something that you can do. And the last thing about housekeeping is Q&A. So if you're tuning in right now, you have the opportunity to ask us questions directly via the chat. And so we'll be checking those out throughout the session. And also at the very end of the session, we'll have dedicated moments for Q&A on the different topics that we're going to cover. So now let's dive into the speakers, the topics, and more. And so I want to start by acknowledging the work of other folks. So many of the topics that you're going to see here are the work of many teams, many engineers, many marketers. And so I really want to express the gratitude for those contributions. And I want to specifically call out two of our backstage folks. So Fermin Dietze and Luis Vega, who make sure that all these operations run very smoothly. We also have our amazing speakers for today, which are going to be Jake Hall, who is in the developer relations team, and also Nana Essilfie-Conduah, who's one of the senior engineering managers over at Hashgraph. So with that in mind, Jake, Nana, I'll give you a chance to introduce yourself. So let's go ahead, Jake.
Yeah, cool. Well, good to be back. Really excited for today's technical community call. I think Nana and I both have some pretty interesting stuff to talk about. I'm going to be talking about one of the new HIPs, HIP 551. So yeah, excited to share some of that information and hear some of the questions that get asked.
Yeah, like Jake, happy to be back. I'm also excited to share about some of the hips that we're working on to block streams and block nodes. Lots of information. Really want the community to be aware of it, and I'm interested in follow-up questions and insights.
Awesome. I think those two are going to be fascinating topics to cover. So, from my end, what I will be covering is the contract builder and more specifically, general developer onboarding tools. So, I'll dive right into it and I'm going to start sharing my screen. And so, what you are able to see here is first the Hedera portal. I want to, just make a brief note about the Hedera portal. We've been adding these tools to make your onboarding experience onto Hedera a lot easier. And so I think many of you are familiar with this particular portal where you can access your credentials to work with your APIs on the testnet. And so if you come over here, now you have this playground and this contract builder available to you. So back in January, we introduced the developer playground, which is that platform that allows you to get started with the SDKs, with the Hedera SDKs on your browser without installing anything. And even in a previous community call, I did a few demos running through different services and type of transactions that you can do. Last week or 2 weeks ago, we introduced the Hedera Contract Builder, which is a playground for smart contract development. So if you're looking to get started with smart contracts, or you're coming from that world of Solidity and contracts, you can also start deploying your contracts on the Hedera testnet without installing anything right from your browser. And so what you see here, it's all embedded in the playground. It defaults to using your ECDSA key. Also, you have the ability to, start fresh, copy your code, share your code, download it once you're ready to take your code into local development. And if I zoom here, one of the things that I also love for developers who are getting started with smart contracts is that this provides standards and templates for you to start doing your contract development. So whether you want to work with a template for simple storage or for understanding getter and setter nature of contracts, you have those templates available to you with a little bit of an explanation. And the great thing is the compilation, the deployment, even the verification and interaction with these smart contracts can all happen on the browser. So you have 2 templates right now. We'll be adding more templates and a few standards that you can work with. So with a matter of just a few clicks, you can deploy your ERC or your HTS-based smart contracts. So just to run us through a quick demo, I want to show you how easy it is to create a smart contract that creates an HTS token. And then perhaps the other function that I'll add to my smart contract is a token airdrop, right? So you can see that the code that was added there, we'll see that there's a disclaimer there. And then the compilation of this contract is all happening right here in the browser. Now I see the artifacts that come out of that compilation process. I can also choose to verify this on deployment or after. So we'll deploy that. And so you see that this is going to deploy and verify my smart contract. And the great thing as well is that in the code editor, this is going to point me to the source files, the source Solidity files that are being imported into the contract that I'm authoring here. So that's the great value of the editor. And now that my contract has been compiled and deployed, I can go to this call view where I can actually execute the functions of my contract. And we've given even default values that you can easily use to make sure that you get to a quick interaction with your smart contract. So in this case, we can call it token name. We can leave these default values. I'm just going to play with some initial parameters here. And in this case, the treasury of my HTS token is going to be this contract that I just deployed. So I can pass a payable amount and executing my contract that is creating an HTS token. And so you see that just with a few clicks, I was able to create a smart contract, deploy a smart contract that also creates an HTS token. And then I can continue modifying my contract and improving my application. So I think this is going to be fantastic for those Web 2 devs and Web 3 devs that want to get onboarded or want to prototype and experiment with their best ideas just on a browser without installing anything. So now you have those 2 paths and those 2 tools available for traditional web development and also for smart contract development. So just wanted to make you aware of those tools. The last tool that I want to bring to your attention is Hedera HiveMind. So I think we've all seen the impact that AI is having in accelerating many flows. We've all heard about agents now, but there's also this GPT, this custom GPT on ChatGPT that you can come and check out. It's called Hedera HiveMind. And this is fascinating because it has a lot of context and information about Hedera documentation, Hedera SDKs, and tutorials. We update it every month. And it can even retrieve information for you from the testnet and the mainnet. So just to give you one quick example, we can come here, grab my testnet account ID, and we can query HiveMind for the balance of my account. So what's the HBAR balance of account on testnet? And so what you'll see is that this is going to search the knowledge base that it has. Then it's going to ask me if it can speak to the mirror node, because it's actually going to go retrieve that data from the testnet mirror node. And then we'll see that it's going to give us the balance of my account on testnet. So it's going through all the knowledge, talking to the connector, confirming that it needs to speak to the testnet mirror node. And then once it retrieves that information with using the mirror node REST API, it gives me a response in plain English that I can understand to see the balance of my account. And it's not only for balances and things like that, right? You can query about most of the mirror node REST API endpoints that we have in our documentation. So you can almost use it as a debugging guide to ask it about transaction information or even smart contract information and much more. And it can also give you great examples and code snippets if you are trying to learn Hedera functionality. So that is the recap or the brief introduction that I wanted to share with all of you today about developer tools. And so remember that you have that playground, that contract builder, and also Hedera HiveMind to help your onboarding journey onto Hedera. So with that in mind, I'm going to stop my screen share. I'm going to open it up to any questions that come through the chat. We'll keep an eye on those. But I do want us to move forward to Jake's topic, which is going to be one of the best hips that I have seen in quite a while that relates to transaction flows. And so, Jake, over to you.
Ready. Cool. Can just before I begin, I've gone full screen, so I can't see my other one. Are you seeing my introducing Hedera 551?
Looks good.
Yeah.
Yep.
Okay. Cool. Well, so yeah, today we're going to be going over one of the recent HIPs, which is going to be rolled out in testnet very soon. HIP 551. And on a really high level, obviously we're going to get into much more detail, but on a really high level, it allows a very much awaited feature to become a reality. You can group together multiple Hedera SDK transactions and execute them atomically on the Hedera network. Now, before I go into the benefits of it, I just want to sort of set the landscape as to what's happening pre-batch transactions. If you as a developer want to provide multiple SDK transactions wrapped up, multiple transactions in a particular user flow. For example, you might want to transfer someone a token and then freeze that account, or give someone KYC and then transfer them that token. Now, what currently happens is SDK users, if you're using the JavaScript SDK or the Java SDK or any of the other multitude of SDKs that we have to sequence multiple Hedera API transactions. So in the example I just gave, transferring a token and then freezing it, you'd have to have separate transactions which execute synchronously, doing the transfer transaction first, waiting for that to resolve, risking it potentially failing and then having to manage that before then moving on to the freeze. There's a risk of sandwich attacks. Let's say the person who you're sending the transaction, the token to, they might be able to quickly transfer that token away to someone else before it gets frozen for them. And obviously that would sort of eliminate the whole purpose of freezing it for that particular account. And it would cause the freeze account token to fail as well. And so, yeah, so there's sort of robust requirements around potential error handling and risk of sandwich attacks. The other common option is you use the EVM in Solidity. So using the Hedera system contracts, you can obviously leverage the native token service. You can mint native tokens, you can transfer tokens, and you can then freeze a particular account for a given token, all inside of one Solidity smart contract. But that adds developer complexity. It requires you to use Solidity, which is obviously, if it's not in your coding set, if you're a pure Java guy, you need to upskill yourself and do that. You need to then sort of manage smart contract deployments. And also, really interestingly, the consensus service, which is not accessible inside of Solidity, is accessible with the SDK. So in the EVM Solidity method, which has benefits to the SDK multiple, the sequencing approach, there's no risk of a sandwich attack. It does execute atomically, but you can't use the consensus service. And obviously the EVM is less scalable than the native services too. So with all of that in mind, that pre-batch transaction landscape in mind, going to now go into what HIP 551 brings and the native atomicity, which is now possible on the network. So first things first, you can get your Hedera API transactions, the transfer transaction, the freeze transaction, bundled all into one single batch, submit that to the network. You now have ability to do it with all of the native services. So that's the token service, that's the consensus service. All of these services you can now bundle into one batch, which isn't possible within just using Solidity smart contracts. It follows ACID principles. So that's atomicity, consistency, isolation, and durability, to make sure that all of them go through, or if not all of them goes through, then it will all fail. And fully native, no Solidity needed. You can do this in any of the SDKs. Again, that's JavaScript, Java, Go, Rust, Swift, Python. Well, maybe we won't be out in Python yet, but there's a lot of SDKs which you can use. And in order to do it, there's a new batch transaction type in the SDK. We're going to go into some code snippets later on. So with that in mind, there we go. And all the transactions are grouped and signed and validated as a unit. But with that in mind, here are some initial use cases which are now totally possible and in a much more improved way. Obviously, this is not an exhaustive list, but immediately soul-bound NFTs. Perfect example. The only way to do a truly low-risk soul-bound NFT, which cannot potentially be sandwiched, is currently by using the Solidity smart contracts. Now you can create soul-bound NFTs using the batch transaction API natively. You can unfreeze an account, transfer the token to them, and then freeze it all atomically. Complex token flow. So again, you can sort of do multiple, I think you can do up to 50 inner transactions, but you can do things like transferring a token and then submitting a consensus message and then freezing it on that account, maybe giving them KYC before. All of these complex transactions, you can now execute them and submit them atomically. As I mentioned, you can also start using consensus services, so you can create topics or submit messages in one single batch. And you can do things like mint a token, transfer the newly minted token to them, and also receive a payment for that particular transaction all atomically. So just a quick comparison, what have we come from to what we have now with the atomic batches. Before HIP 551, you need to have multiple independent Hedera API calls if you're using the SDK. Partial failures are possible, so you need to then have your own custom logic to sort of go, right, if this fails, don't execute the next one, or maybe do a retry if the first one fails. All gets a bit too confusing. Smart contracts are often required, and for the consensus service, it's just totally ruled out. No consensus service support in the EVM. And all of that sort of bundles up to make the developer experience a bit more difficult. Whereas after HIP 551, everything is ACID compliant, submitted into a batch, executed on the network. It all goes through, or if anything, if one fails, it all fails. So there's no, the error handling is less complex because you just rerun the same transaction. Smart contracts basically wouldn't be needed in this instance. Consensus service fully supported, and it's so simple using the SDK. I think we've got some snippets in here now. So there's two things that you need to sort of understand when it comes to creating a batch transaction, and that's that you have the inner transactions, which would be your typical SDK transactions that before HIP 551 you have to execute synchronously. With the inner transaction, all you need to do is you just take an existing, for example, token mint transaction, pass all of the methods as you usually would, set all of the methods as you usually would, and then add this batchify method, passing in the client that you're going to submit the transaction with, and a batch key. Now, the batch key, this adds an element of security against potentially malicious nodes. But essentially what the batch key does is anytime a inner transaction is signed with a batch key, that batch key then must be that batch key must then be signed on the outer transaction when it's actually submitted. But all that you need to do is in these existing flows, take your initial class, add this batchify. It is asynchronous because you're signing the transaction, so you need to await it. But you can obviously do many inner transactions, and then using this new batch transaction class, you then add the inner transaction. You just take that from what's been done previously, sign it with the batch key, or the multiple batch keys if you've got a different batch key for a different inner transactions, and then just execute that to the network as you usually would. On the mirror node side of things, there's nothing really new, but we've just sort of updated the mirror node so that the existing transaction ID API returns the full batch structure. So it'll include all of the inner transactions, the batch keys for the inner transaction, and the consensus timestamp for the outer transaction. And then you can also access the inner transaction records as well to get some more information there. To wrap everything up, I know I've been pretty quick, but HIP 551, you can now have atomic Hedera, multiple Hedera API transactions. Basically anything in the SDK you can wrap up atomically, except for the schedule service. You can't do the schedule service. It eliminates a lot of smart contract complexity for many of the use cases, which is really great for a lot of the a lot of our projects in the ecosystem are very, very pro SDK. And again, for the scalability side of things, the SDK and the native services are so much more scalable than the EVM, and much nicer user experience from the customer side. If you're getting the customer to pay for transactions, now they just need to sign it once. More secure with the ACID principles. And yeah, that's basically it. Again, like Ed said, happy to take on any questions for this. And excited to see really what people could do with it once this gets in the hands of the developers in our ecosystem.
That's amazing. Thank you for that great overview, Jake. I thought it went fast, but it was very informative to receive this set of updates from you on HIP 551. I think we'll give an opportunity for people to keep adding questions in the chat for those questions to come in, and then we'll tackle questions maybe for all the topics at the very end. I do want to move on and give Nana an opportunity to let us know more about block streams and block nodes. And before we move to Nana, I do want to do a quick plug about the work that was done for those developer tools that I mentioned before. So the contract builder and the developer playground have been developing collaboration with Kabula, which is a project from our community and ecosystem. So that has been a very fruitful partnership that resulted in great tools. And then the other call to action that I want to provide here in this quick recess is developer Q&A. So every week, if you're a developer and you're building, every week on Thursdays, we do have developer Q&A sessions that are open sessions where you can come in. You can treat those as office hours to discuss maybe issues where you're stuck or you want to learn more about. We have folks and experts that can help you with those. So keep those points in mind and join us for the upcoming Dev Q&A next week. So with that in mind, Nana, let's talk about block streams and block nodes.
Yeah, nice content, by the way, Jake. I appreciate the update on batch transactions, and I'm excited to see what the community will do with that. But as Ed mentioned, my name is Essilfie-Conduah. I have the pleasure of serving as a director of software engineering at Hashgraph. And today I get to talk about block streams and block nodes. So some of you will have had the pleasure of watching Jasper Potts and Richard Bear's presentation of this at HederaCon. I recommend that you watch that in advance. And I hope to add on to this, but want to kind of repeat a couple of things there, but also give you another view of the projects that are entailed here. So let me run you through what we're going to go through. So I'll give you some context of why we're doing all of this. I'll highlight the fact that we have multiple streams today, and we're trying to move to a unified stream of block streams, what it might look like to cut over from our current multiple streams in records to block streams. Then I'll highlight the importance of block nodes and what they're serving. I'll hopefully do a good recap of all of that, and then really touch on timeline and call to action. I know some of you are already asking about timeline, so I'll get to that. So before I share anything, some of you may be wondering, why do all of this, right? The network is operating great. Batch transactions are coming. Why all this change? What's this necessary for? As a group, as an open source initiative, we're always pushing for a couple of things. And so to me, the motivation is at least these three things, right? Decentralization, transparency, and ecosystem enablement. So decentralization, as part of the Web3 ethos, we all believe in sharing that power, that information. And we've started something, and we're trying to guard and protect the network. But our long-term goal is to, as much as possible, decentralize everything. And so that means looking at places where there might be centralization of ownership or data or anything, and putting that in the hands of the community where possible. We also want to push on transparency. We want to make sure that everything the network is doing is exposed and available to anybody to look in, right? You might hear sometimes say, trust nobody. That means that, sure, you're seeing all of this information, you hear about trust, but we encourage you always to verify it yourself, right? That should be a basis, right, for Web3. And then ecosystem enablement, right? We don't want you to have to wait for the higher ledger to develop something and then, the Hedera network to deploy itself. Where possible, we want to put the power in your hands as operators, as users, to be able to build the additional services and capabilities that you want. So other than EVM upgrades to the networks, this is one of the few projects that has a lot of HIPs contributing to it. So I'm just mentioning them here so that you guys can take a look after. We have HIP 1056 block streams, HIP 1200 hints threshold signature scheme. And so this is adding trust, increased trust factor to the network. 1193, which is going to talk about how we move from records to blocks. I'll talk more about that. 1081, which is block nodes itself. And then 1137, which is hopefully how block nodes can be discovered. So let me talk about the fact that today we have multiple streams, right? In our current network data specification, what's going on with the network every time you submit a transaction, there are multiple streams of information coming out. And one of the main ones that we'll focus on is record streams, which if you refer to HIP 435, gives more information about that. Interestingly enough, that HIP is the 6th version of that record stream. So you can see that we continue to iterate. But in today's network architecture that uses record streams, this is kind of what it looks like, right? On the left side, you see the consensus node. This is where your SDK transactions are being submitted to. This consensus node is gossiping with other consensus nodes. And what's interesting is that coming out of that consensus node is a couple of streams of information. I'll start from the top. We have records. So records are, like the name kind of suggests, a record of the transactions. And so it's what you submitted in that transaction, but it's also the impact of it, the output, right? So if you did a crypto transfer, it will be the fact that you intended, or I intended to send Jake a couple of HBAR, and then Jake hopefully intended to send it to Ed, right? And so the output of that would also be part of that record to say that Ed received the culmination of that HBAR. We also have sidecar files, which right now are mostly being used for EVM data. So things about, what happened in the EVM, how much gas was consumed, all of that interesting information, as well as signature files. And so each consensus node signs its work, right? And so it needs to share that signature file to be able to validate the record and sidecars. We have a second stream, which is the event file stream. And this is really all the information about consensus, right? Everything that allowed us to come to consensus when a node received it, things about the judges and the witnesses, all of that information is in there. We used to have a stream about account balance, and this was literally a file with every single account on the network, its HBAR and its HGS tokens. Thankfully, we deprecated that because you can imagine as the network grows, that wouldn't necessarily scale. And then each of these consensus nodes are also periodically outputting saved state streams, right? And so this is a snapshot in time of the Hashgraph state and pushing this up. All of these are going to cloud buckets today in Amazon AWS and Google GCP. And then from there, mirror nodes and other people that want to pull this information are downloading these individual record files, the sidecar files, and the signature files, right? And so you can see there's a bit of work there. They have to do some coordination because specific sidecars represent or correlate to certain record files, and then the signatures represent the work that the consensus node did. And then we also have additional processes around deduplicating the stream. If you think about the network today, if my count is correct, I think we have 32 nodes. And so there are, in many cases, 32 copies of each of these files. And so it gets really big. And so being able to reduce that cost is important. So record streams was our initial attempt to expose the information around the transactions and state and network. But you can already see that there are some places where we can probably improve. And if we're honest, part of this is a little centralized in the middle there. And so the implications of these are, data costs. Mirror node operators have to pay to be able to download all of these files from the cloud bucket, right? In terms of scaling, as the network continues to grow, imagine 10,000 TPS all the time. We've been a couple of years in. The last time I checked, it was 72 billion transactions. This is all information being stored in the cloud and needing to be output by the consensus node. And so there are scaling challenges here. The current infrastructure also makes it so that there are certain things that only the consensus node can do. Only the consensus node has the true representation of state, and only the consensus node can service what we call reconnect requests. And so this is when a new consensus node is joining the network, or maybe it falls behind. It needs to get the latest information around state and what's going on. And usually it talks to another consensus node. And then also within the record streams, the schema is incomplete. And so sometimes the mirror node gets the majority of information, but it may miss something, or it may there may be some internal state of the consensus node that wasn't put inside the schema. And so that never makes it out to the rest. And so, our architects, in particular, Jasper Potts, I want to say like 18 to 19 months ago, was thinking of this, and he came up with this idea. What if instead of having multiple streams, we had a single stream? What if instead of lots of duplication of information, we had it unified and really streamlined, right? And what if instead of having to push it to cloud buckets, we made it so that anybody could receive these block streams and could have it, right? And a lot of capabilities could be in that block stream. And so that's what block streams are. In HIP 1056, we explain this a lot more, as well as the new signature schema in HIP 1200. So some characteristics of the block streams, like I mentioned, optimized streaming. And so the block streams will have the complete information around inputs, outputs, and it will be deduplicated, right? So that we try as much as possible not to repeat information, so that stream is small, and the weight is, or at least the size is a lot smaller, right? It will have proof support. So an interesting factor is, as much as possible, a block will be self-contained with maybe one or two publicly available pieces of information like the ledger ID. But a block itself will provide its own proof that you will be able to verify. So again, you don't need to trust the block, but the information that you need is there and you can verify it, right? State transparency. So now all of state as well as changes will be present in the block stream. And so you will be able to confirm in that scenario that, Ed actually got that HBAR that was supposed to be sent to him in that block. We hope to make this decentralized. And so now anybody can maintain live state, because by reading the block stream, you can produce that state and see everything that's going on. But you can also do some nifty things that I'll share about, which would be like filtering the block stream down to something that is important to you. So you might not care about all transactions, and so you'll be able to filter that down, but still be able to prove the authenticity of the block stream. It's also optimized for streaming. And so before, even though we called it record streams, it was really a process of continuously sending record files. And so this could be large if you had large transactions per second in that time space. In this case, block streams allows you to send little bits of information over time, even before the block is over. And so what does a block stream actually look like? We try to optimize for predictability as well. And so let me start from the left. The block proof item, each of these items, we're calling them block items. And so the block proof item there represents the last item in the previous block. And so after that, you would always expect the next item to be the first item in the next block. And so a block header signifies the beginning of a block. And so that block header block item is going to tell you the block number, maybe something like the version of the schema that is being used, so that you can understand how to process it. After that, you have the round and the event header block items, and these are going to give you sort of metadata information around consensus and what's going on. Then you have the event transaction. And so this is the transaction that a user specified in their SDK to submit. Then the following two items are the transaction result and the output. And these are a combination of the impacts on the network and the actual outputs of that transaction, right? Then we have a new item that we hadn't exposed before in record files, which is state changes. So here you will see the exact change to Ed's account in this example, where you'll see that Ed's account is fully represented and it's not just the delta. So let me kind of repeat that part. So we had a choice of, do we do the diff of Ed's account or do we give you Ed's whole account? And we thought that it was more important to give you the whole entity, and in that way you don't have to go back to Genesis to find an account that was created right after Genesis, right? And this is an issue that happens in the mirror node when a new operator tries to start up. They have to get a whole big snapshot of all of the information. In this case, if an account hadn't been touched since Genesis but was just updated today, you would have that whole entity in state represented in the block stream. And so that next item after that is trace data. So this is a new kind of block item where information that's not necessarily essential but could be filtered out, you might want to put it here. You might put like the full error message if you wanted to, or something that really talks about the innards of a transaction. Maybe it's not essential for every explorer, but it's important to some people. But once you have this block stream, this might be a place where you might decide to filter out. So after that, you might have some non-transaction related state changes. And then finally, you'll end the block in a block proof. And so the block proof will be the location that will have all the information that will be able to prove the network, the blockchain up to this point, and this block specifically. And so as you're looking at the stream, you'll see that for every transaction, you have a repetition from event transaction to trace data. For every event, you have from event header to trace data. And for every round, you have from round header to trace data, right? And so what does the architecture of the network look like now? If you remember the similar diagram before, you had a ton of streams coming out of the consensus node. Now it's just one. It's just one simple stream that you can think about and have to worry about. But instead of going to a cloud bucket, it's now going to this new node that I'll talk about a little later, which will be the block node, right? From that block node, you'll also be able to continuously stream out that same block stream that was output from the consensus node to the mirror node, to other block nodes, or to any other application that wants to get block streams. And so this is our new approach to expose transaction, state, and network information, right? And it's really focused on transparency, making sure that everything that is changing and going on in the consensus node is in there, and allowing ecosystem enablement of all the features and ideas that we haven't yet thought of or can't think of. So I showed you what the block stream looks like when it's actually being, written out, right? Or serialized. But there's a different conceptual model that allows you to do the things like proofs. So we use Merkle trees a lot. And so a block can be represented by a Merkle tree, in this case, with 8 leaf nodes, right? And so the first one at the bottom would be the block root hash of the previous block. So once you have a block and you've been able to calculate the hash of that, you take it, and that's the first component of this conceptual node, right? Block. The second node there is the state Merkle tree of the previous block. So at the end of the previous block, whatever the state hash was, that's that component that goes into the node. The third one is the consensus headers. This is the combination of the event, or actually the round and the event headers. The input Merkle tree is the aggregation of all the transaction inputs. The output Merkle tree is the aggregation of all the results and output information that you saw before. And then state changes, similar, and then trace data. And so once you're able to calculate all of these, all the inputs to this node, then you build up your Merkle tree, you take the hash of each of the items, you get the next internal hash, and you take the hash of that, and eventually you build this block hash. This block hash is what every consensus node actually signs, right? And then this is what is used to prove it. And then what's interesting here is that this is where you start to see filtering capabilities, because if I receive a block stream, but I don't want to hold on to everything, I can replace the actual data with just the hash. And in this way, the next person that gets the block stream from me can still prove the authenticity of everything else in the block stream, but they don't need to have all the data or the actual data, because now it's a certain block item is represented by its hash. And so let me blow that up a bit. Hopefully you can see it. So what I just showed you before, the 8-leaf nodes, you can see it at the top right there, but you can see that the first node connects to the block hash of the previous block, but you can also see how the components within the block stream that I noted are built up into each of these root nodes, right? So you see the round headers and the event headers, you see the transactions, you see the results and the outputs and the state changes, and you see the calculation that is done to be able to basically calculate and represent a block. And so maybe simplified a little bit, let's look at the blockchain. I mean, you've heard me before and others say that the higher ledger and Hedera, its deployment is indeed a blockchain, right? This is another instance of confirming that it is, right? So let's take block 99. Its root will link to the previous block. Block 100 will link to block 99. Block 101 will link to 100. And what's interesting is that if you take the proof of block 101 and you verify it with its TSS signature, you have essentially proved the whole history of the network at any block in time. Another way to put this is that, let's say you were interested in something in block 99, but you didn't have the proof for block 99, you didn't have the proof for block 100, but you received the proof for 101, you can be assured that block 99 is as stated in the blockchain. You could essentially take a state snapshot right before block 99, apply all of block 99's details, apply all of block 100's details and 101's details, and it would map to the proof that you found in 101. So this allows operators to do a lot of interesting things, but it also increases the trust in the information that's coming out of the network. So I've mentioned a couple of proofs, but let me highlight them properly. So in the block streams, we're exposing a few new proofs, right? So the hints, or the hints proof highlighted in HIP 1200, it's literally a proof that the given consensus nodes that have come to consensus are truly part of the chain of trust of the ledger. So what will happen is that at Genesis, you had a couple of consensus nodes that were there. Then over time, consensus nodes are added or removed, but the consensus nodes present have to agree on that. So today, you usually kind of just take for granted that consensus node X is part of it, right? But we want to be able to provide you the proof that consensus node X was agreed upon in addition to the roster of the lists of consensus nodes. So that's the new proof there. So that it gives you this, it gives you the ability to add more trust by verifying it yourself that a given consensus node is actually truly part of the chain of trust. Then we have the block proof, which I've spoken about a bit, proves the whole blockchain, but it proves the components of the block were as stated, that all the said transaction state changes and everything are actually in that block, right? Then there's a new type of proof that we came across as we were doing this, which is the block contents proof. So this is the ability to say that within block 100, there actually was a crypto transfer from myself to Ed, right? Or I could say within that block, there was actually a state change of Ed's account from, you know, 1 million to 1,100,000 because I sent him 100, right? You can prove within that block without having to worry about, you know, the state proof that we'll get to, but you'll be able to prove within that block that the contents or some action happened, right? And then finally, the one that we've all been waiting for a while which is state proof. So you will be able to prove that at a given block, the state of the network was as such, or that within that state, there is a certain entity with these properties. And so all of these proofs are now exposed within the block streams, and anybody will be able to take that block stream and verify those proofs. So I've shared a bit about where we were with record streams, where we want to go with block streams, but how do we get there? It's a lot I've shared, and we're still working on it. But how do we get there? It's a coordinated transition, right? So to make things easy, shockingly, we're going to keep using cloud buckets a little longer, just so that the transition isn't too painful. So essentially what we're going to do is that in the cloud buckets, we're going to add another path that is focused on block streams, right? So operators will now have an endpoint where they can go to pick up the block streams as they're coming out of the network. This means that consensus nodes will be updated to produce block streams only and no longer produce record streams. It also means that mirror nodes will be updated to parse and handle block streams only going forward. And I'm stressing this part because it's vital and very important to every operator of a mirror node or every operator consuming record streams today, that they update their code or they update their mirror node to a version that can handle block streams. If you don't, and I stress this, if you don't, your view of the network will essentially halt. The network will be fine. It will still be processing transactions, but your view of it, all the information that you're getting, will stop because the record streams will stop. The last record file will be followed by the first block within a block streams. So you want to make sure that as an operator, you're ready for this transition. This is why I'm exposing it to you now. As users, you want to make sure that if you're using any of these operators, that they're aware of it and that they're updating. But to make sure that the transition is good, we'll have sort of like a validation period, right? We want to make sure that everybody's aware. We're not just going to do that today. This is also why we're using the Cloud Bucket to give a bit more time for everybody to update. We don't want to disrupt any business. We never do things at the sake of network integrity or applications that users are using. So I've said a lot of things. You know, I've spoken about an optimized data stream. I've highlighted new proofs and verification capabilities, even stream filtering, right? But I kind of glossed over what block nodes are, right? So let me get back to that, all right? So block nodes introduced in HIP 1081 and also a bit more details in 1137 around discoverability. They're essentially our take at decentralized block and state storage, right? So some of the properties or characteristics of a block node is anyone can run a block node. Unlike a consensus node today, anybody could run a block node and store network information. The block node will be able to service some existing network services today. I'd mentioned reconnect before. Now a block node can serve the reconnect feature that a consensus node does today. And this is good because it alleviates the consensus node from having to worry about that. Consensus nodes no longer have to worry about the bandwidth that's spent on reconnect because a consensus node can go to a block node for that property. Block nodes will also manage state. So this will be another location where live state of the actual hash graph will be represented, and block nodes will be able to generate state backups. And so again, another thing that the consensus node doesn't have to do, so that it can scale out and focus on just managing your transactions and come into consensus. Block nodes will have the ability to verify and produce proofs upon request. One of the things that we're also trying to do is ensure that there's third-party customization support. So you'll have the ability to do what is provided, but as operators, you can extend the block node to do what you like. For good security reasons, you cannot do this on the consensus node, but with the block node, you can kind of customize the features if you like, pick and choose, but also add. And also we're excited to hopefully present some monetization possibilities. And this will, again, be up to operators. You can use Web 2 existing rails, or you could explore Web 3 payments. What would it look like if you're streaming block streams out of a block node and it's paid in HBARs or anything else, other tokens, right? But again, the power is within the hands of the block node operators to do what they would like. So quickly on the APIs, so you'll have block-related APIs to stream blocks. Each of those block items, as I was talking about before, you don't need to wait for a whole block to be ready. You can start streaming each of those items, and this allows for low latency scenarios, and so you can get your information quickly. Block nodes will also serve random access requests of blocks. You'll be able to query a block node to understand, what's its earliest block and what's its latest block, so you know what to do with that. You'll be able to make requests for state snapshots and get details around state, and then also the proofs that I mentioned. So a quick view on the internal architecture of the block node. I'll quickly go through this for those that are interested. But a block node will have the ability to receive block streams from multiple producers, right? So that comes into a process that handles what that we call sort of like the stream publisher. So internally, we have a process of streaming the block items to different parts within the block node. And one of the first stops that it does is the block validator. And so this is where it's going to verify the proof within that block. So before we store anything, we verify the block. And once that's verified, we pass this along to, say, a block provider. Block providers are responsible for both storing and querying internal block information. So we'll store the blocks, but we'll also service them up when random access queries are made for specific blocks. In the same way, after verification, a state manager will store state and also respond to query requests. We'll also have a remote archiver that will allow an independently operated block node to archive its information somewhere. This is important for disaster recovery scenarios, but also redundancy as well, right? So now that you're able to sort of mix and match different capabilities of a block node, it's important to highlight the different types. You'll hear of a full history block node. This is a block node that stores all of history and responds to API requests. This is the typical one that you'll see in production when it gets there. There will also be archive-only block nodes where they are only focused on storing. They will not expose APIs, but they're really there, like I mentioned, for disaster recovery, redundancy, and just they're focused on the storage, right? Tier 1 block nodes in that architecture will be block nodes that receive block streams directly from consensus nodes, and Tier 2 block nodes will be those that receive it from anybody producing block streams. It can be a block node, it could be any other application that's written, but it's important to highlight those. So quick recap, I showed you, or I highlighted at the beginning, today we have multiple streams. I highlighted how the block streams unifies that, brings in a lot of capabilities. I shared our intermediate step of moving block streams into Cloud Buckets first to sort of support the easy transition over. And then I showed what the final state should look like with block streams in block nodes. So illustrating that graphically, I've kind of expanded or elongated the consensus node on the left. So the same transactions, on top is what it is today, below is where we want to go. So essentially you'll see, we compress those streams, we make it one unified one, we replace the Cloud Buckets with the block node, and then we have tiers of block nodes as well. And that transition period, as I mentioned, in between would be sending the unified block stream over to Cloud Buckets and then eventually replacing the Cloud Buckets with block nodes. So somebody asked about when will block nodes be deployed, when will block streams be live? Are we there yet? Not yet, but we're working hard. And so this might be familiar to some people who watched the HederaCon presentation, but at the end of last year, we shared the preview of block streams. And so today, for the last couple of months, preview of block streams has been running through all the environments, PreviewNet, testnet, and mainnet, to help us begin to test this, to make sure that we have that full representation that we started and spoke about. We've been pushing hard to get the blockstream hips and related ones finalized. So I can actually share that the TSC approved the blockstreams hip, and the Hiro TSC approved the blockstreams hip, and the Hedera TechCom accepted it. And so we're working hard to get all those other hips that I mentioned through the Hiro Ledger open source process, as well as the Hedera TechCom process as well. And so once all of that is sorted out, once our testing is sorted out, we'll be moving, record streams over to block streams in those Cloud Buckets. We also hope to then deploy block nodes and have them live in parallel. And the block nodes will sort of be upgraded similar to mirror nodes, for example. So we have a cadence right now, I think, of every 2 weeks. And so a new version would come then. It's not connected to the consensus node milestone upgrade. So it's not a big overall network upgrade, and block node operators can upgrade the block nodes anytime they like, with some caveats of, if the schema changes, then you want to do some coordinations there. But hopefully before the end of the year, we're aiming to then make all of this transition and then stop the production of block streams into the buckets, and mirror nodes, as I mentioned, would have to look to a cloud, to a block node to switch over and get their information there. So finally, call to action, where can you get involved, right? We would love and ask and encourage community engagement across the HIPs. Please review them, please comment on them. It's really important that these HIPs satisfy the community and the scenarios that you're going through. And so we really appreciate and are interested in your views. Contribute to the open source Hiro Ledger. The consensus node, the block node, the mirror node, and all the other products are all open source. So you can open tickets, you can submit PRs, And for the block node and others, we are hoping to start Hiro-related community calls. And so we'd love to have you join and get your perspectives there. For the block node, we're trying and exploring this new process of having a beta program. And so we'd be looking for early testers and operators to run a block node early on and see what it's like. We want that developer experience to be really easy and clean, and everybody, like I said, anybody to be able to run it. And then finally, at least on maybe a selfish plug here would be, share open hiring roles, right? At Hiro and at Hashgraph, I know the platform teams, my team, the block nodes team, mirror node and smart contract team are all hiring. So if you know any, specifically on this side, if you know any really good experienced Java engineers with, core Java competencies, please send them our way, and they would help, speed up things. And we love diversity of thought as well. And so getting these bright minds in there would be great. So that was a lot, but happy to answer any questions on this and take it up with Jake as well. Thanks, everyone.
That was fascinating. Thank you so much, Nana, for that deep dive into block streams and block nodes and all of the additional concepts and considerations that come along with those two. So I do want to start with a couple of questions. The first one touching on, or is going to be very relevant for mirror node operators. What will be the transition, or what will that transition look like from record stream to block stream? And will there be a developer preview for the block stream or any additional tools? Because I know you did mention the testers, early testers program. Will there be a preview? And if you could comment on what that transition period and process will look like.
Yeah. So like I mentioned, there's the preview block stream. So that's already there. If you are an operator that is already pulling files down from these cloud buckets, or anybody that wants to, you can pull down preview block streams today. It's not fully complete, but the structure is there for you to get early ideas. I can also say that the mirror node team has already been hard at work processing these and being able to support them. So it's not doing it in production, but the mirror node open source code base, as you can see if you check in, is already able to handle some of these preview block streams, and it's getting updated. So anybody could run a mirror node. You could run it in your test scenarios, and you could process the block streams. The mirror node is also working on updating internally the ability to pull down the block streams from that cloud bucket that I mentioned. And so, early adopters, early testers will be able to have support for that. And if there's any gaps in the tooling, again, we'd love to hear and be able to try and provide that for you. But the team is working on it, and we hope the transition should be easy for an operator who's upgrading. Essentially, they shouldn't see a difference on the end, but the mirror node itself will have those capabilities. If you're not running a mirror node yourself, then you'll have to be responsible for updating your logic to move from records to block streams.
Excellent. Now, another question on the block stream in relation to the Hashgraph consensus algorithm. Could you comment on the relationship between those two? So where is the Hashgraph consensus algorithm? Where is the block stream? And what's the connection between those two?
Yeah, so the Hashgraph algorithm is still on the consensus node. It's still the logic in which each of these consensus nodes are processing and coming to agreement on these transactions. Where the connection happens is that the details of that are now going to be fed into the block streams. So those event information and the round information that I showcased, that's one of the locations where you're going to have like a view into all of the details that a consensus node went through to come to consensus, right? And the details that the inner workings are now exposed through the block streams. And so one of the goals of the block streams is that you should be able to read a block stream and replay the activity of the network, right? And so you should be able to say that, hey, consensus node 1 saw this and did this, consensus node 2 saw this and did this. You should be able to replay that upon reading the block streams.
Excellent. Thank you for that clarification, Nana. Jake, coming over to you with a question. Well, there is a comment here for Nana. Someone is raising their hand to be part of that early testers program. So yes, I do agree that it was a very insightful presentation by Nana today. All right, so Jake, there was a question as well on batch transactions. If you could comment on how do you see batch transactions reshaping DeFi strategies for the ecosystem, especially around the areas of composability and gas optimization?
Yeah, so I think here, definitely batch transactions, it's not going to totally eliminate the importance of smart contracts. Obviously, smart contracts, they're highly customizable. And I mean, for example, you wouldn't see any decentralized exchange sort of migrating their smart contract logic over to batch transactions, at least anytime soon. I mean, that's just from my initial understanding and testing with the batch transaction API. So it's sort of what batch transactions are doing. I see them as more of like an intermediary between the traditional usage of SDKs, which is great for single transactions, but when it gets to sort of do multiple things at once, there is slight more complexity than if you want to sort of string multiple sequences together. It becomes a bit more complex. Whereas in terms of really low level customizability and programmability, I think there's still the advantage on the smart contract side of things. So for a lot of stuff which we're doing on DeFi, I still think we'll be interacting with smart contracts. But definitely when it comes to, I don't know, say you're an NFT creator platform and you want to create soul-bound tokens, it just makes it that much easier to do it natively, that much cheaper and that much more scalable to do it within the batch transaction environment. But again, I'm really excited to sort of have this in the hands of developers, and maybe they'll totally prove me wrong, and we can sort of build entire protocols using the batch transactions. I think really that's the beauty of having technology being that tech layer, because the creativity is in the hands of people watching the stream.
Amazing and well said, Jake. There's another question coming here from Louis Fourier, which is, for batch transactions, what happens when an individual inner transaction fails? Is there a rollback of the other transactions? So if you could
yes,
comment on that.
That's part of the acid sort of what would be the right word? The acid approach, the acid lock. Anyway, what the acid transaction is atomic, consistent, isolated, and durable. And essentially, yes, if one of them fails, the whole transaction will just fall back. So if one of the inner transactions, for whatever reason, fails, I mean, it's pretty unlikely because of how robust the Hedera consensus algorithm is. But assuming one of them does fail, none of that state will progress forward. It'll just revert back to the initial state at that point in time. Whereas in the case of the traditional approach using SDKs, you don't have that atomicity and that sort of durability, in the sense that if you do an unfreeze transaction and then you transfer the token and that transfer token fails, then the account's been unfrozen. You then need to refreeze that account to get them back to the original state, which just adds so much complexity. So to summarize, yeah, inner transactions, if one of them fails, everything rolls back. That state does not progress. I'd imagine it still costs a fee, but it's much easier from the developer experience, and also from the risk perspective, much lower risk.
Excellent.
And Nana, is there any? Do you want to add anything to that, or did I describe it well?
Nah, you're solid. You did it.
All right.
Love it. All right, guys. So we are a few minutes beyond the top of the hour, but I do want to thank our speakers again. Nana, Jake, thank you so much for those insightful presentations and topics. I also want to call out once more our backstage folks. So Fermin, Luis, thank you for making this operation run smoothly as always. And to you, the viewers and the community, always thank you for tuning in. Thank you for the feedback, and looking forward to seeing you at those developer Q&As that happen every week and at our next community call. So with that, have a fantastic rest of the week, everyone. Thank you.
Take care, everyone.
Thanks, everyone. Take care.